Hey, this is your instructor, Peggy Jankovic, Dr. Peggy, and I know that a lot of you were a little bit confused by induction yesterday in class, which is normal. I think that's kind of the universal Math 100 student experience. But after a bunch of the questions I got after class, as well as in my office hours today, I've decided to put together this video with a bunch more examples and more explanations. So just to recap the kind of general philosophy behind proof by induction, the idea is we want to prove some kind of a claim for infinitely many integers. So, that can be one of those ones where we're trying to show that a certain number is divisible by another number, or some kind of inequality or some kind of equation that depends on an integer. And we want to show that it's always true. And so that would mean that it has to be true for, let's say, if it's one where it starts at 1, we would have to show that it's true for n is equal to 1, n is equal to 2, n is equal to 3, and so on, forever. Because we can't actually do that, what we'll do is we'll set up ourselves like a philosophical, logistical framework where we can say, well, we can check directly that it's true for the very first one. So that's the base cases. So base case, we verify directly for the first statement. And I say statement because sometimes it is an inequality or an equality or something else. This is just kind of the general idea. And then the inductive step is where we say that anytime one version of the statement is true, then one directly after it will also be true. So anytime the statement is true for, let's say, n is equal to k, then the next one, so n is equal to k plus 1, will also be true. So here, if we're looking at this list of kind of labeled statements, you've got your n is equal to 1, n is equal to 2, and so on. For the base case, we check that one directly. And then what we do is we show that anytime n is equal to k works, it will directly imply n is equal to k plus 1. That's enough to show that every single one of them is true, because we've now allowed ourselves to kind of introduce this implication arrow. And so, because we've done the inductive step, it means that if n is equal to 1 is true, then the next one, n is equal to 2, is also true. And then the next one, n is equal to 3, is also true. And same with 4 and 5 and so on forever. So that's like the power of the inductive step, is it allows us to say that as long as something is true, the next one will be. And so because we've started it all off with a base case that works, now all of them will work. So that's the idea. I think the two main things I notice students struggle with induction problems are, first, like that kind of, like the purpose of it. So like why we're doing this. And then also just sometimes like the algebra and the techniques are just new. So, or at least different motivations than you might have used the same techniques previously. Okay, so here I've got 7 new examples to go through, as well as the original 4 from the skeleton notes. I'll just redo those with however much time I've got ahead of me here. So let's get going. For our first one, we'll prove that by induction, the number n cubed plus 2n is divisible by 3 for all natural numbers n. So that means n greater than or equal to 1. Well, if you wanted to think about what those numbers actually are, I've listed some of them here. So the first one, n is equal to 1, is the number 1 plus 2. So that's 3. N is equal to 2, that's 2 cubed plus 4, so I guess that's 12. N is equal to 3, that's 3 cubed plus 6, so that's 33. I'm not going to keep adding these. And then n is equal to 4, that's 4 cubed plus 8, and so on. Just plugging in these different values in for n. And we want to show that no matter what we choose for n, that number will always be divisible by 3. And so what we'll do is start off with our base case and then do the induction step. So, base case, when n is equal to 1, we get, like we already saw, 1 plus 2 is 3, which indeed is divisible by 3. Now we'll do our inductive step. So here we'll assume that k cubed plus 2k, whatever that number is, it's divisible by 3. And so now we want to show that the next one is divisible by 3. Now, this is optional. You don't necessarily have to do this, but if it helps you to understand more concretely what's going on, we can also use the fact that if it's divisible by 3, that means like the definition of a number being divisible by 3, that means that there is an integer m, let's say, such that we can write that k cubed plus 2k is equal to 3 times m. So it's like saying that we can factor a 3 out of k cubed plus 2k and be left with an integer, not like a weird fraction or something. Okay, so now we consider the next number in our list. So that's the one that's k cubed, or k plus 1 cubed, plus 2 times k plus 1. So what we want to do is we want to rewrite this so that it's clearly divisible by 3. And you know what, I'm going to do a lot of writing here so that all of this is down. So we want to rewrite this is clearly also divisible by 3. And we'll have to use the fact that the previous one, k cubed plus 2k, is divisible by 3. The whole point of the inductive step is that we do have to use the assumption in order to prove the new statement. Okay, wait 1 second. I've got a cat trying to sit on me. Okay. Okay, so here, what we can do is we can start off by taking that k plus 1 cubed plus 2k plus 1 and rewrite it so that, rewrite it so that it's expanded. So let's write 2k plus 1 cubed plus 2k plus 1. Expanding the k plus 1 cubed, that's k cubed plus 3k squared plus 3k plus 1. Here, I'm just kind of making things faster by using Pascal's triangle, if you remember that. Pascal's triangle tells us what the binomial expansion coefficients are. We always have 1, 3, 3, 1 for the cube. Just a little trick I use so I can save some time. Okay, and then we still have 2k plus 2. Now looking at this, I'm seeing that k cubed plus 2k show up. We've got k cubed plus 2k. And so if we reorganize our terms, we've got k cubed plus 2k, which we already know is divisible by 3. And then we've also got 3k squared plus 3k plus 3. Oh, and that's all divisible by 3 as well. So our first two terms are that k cubed plus 2k. That's divisible by 3 by assumption. And then those last three terms are also divisible by 3. And so that means then that this new one is all divisible by 3. Or you can say that, yeah, just this whole thing is divisible by 3. If we want to show directly using that 3m thing that we've got set up already, you can write it as 3m plus k squared plus k plus 1. So that's divisible by 3. Therefore, by induction, we can say that n cubed plus 2n is divisible by 3 for all natural numbers n. And that's it. So here we can see that, again, we had to use our base case to start the chain of dominoes, like I said in class. And then we've got our inductive step that tells us that as long as one number of that format is divisible by 3, the next one will be. Using that directly here, maybe I'll underline that assumption to make it extra clear. Yeah. So here we're using the assumption to show that the next one is also divisible by 3. So there we go. There's a cool divisibility question. Now this next one is one that's kind of like one of these general sums. Here we want to prove by induction that 10 to the power of 1 plus 10 squared plus 10 cubed and so on, all the way up to 10 to the power of n is equal to 10 over 9 times 10 to the n minus 1 for n greater than or equal to 1. Okay, so same idea as before. Let's check our base case. When n is equal to 1, that means we only have one power of n on the left-hand side. So we just have 10. And then on the right-hand side, we have 10 over 9 times 10 minus 1. And that cancels out. That's 10. We're good. Cool. Okay. Now for the inductive step, we will assume that the sum of these powers of 10 up to k fit the formula. So 10 to the 1, 10 to the 2, plus dot, 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 plus 10 to the k. Assume this is equal to 10 over 9 to the 10 times 10 to the k minus 1. And then we want to show that for n is equal to k plus 1, that also fits this formula. So I'll write it what we want to show. So that means that instead of stopping at k, we get an extra term because we go all the way up to k plus 1. So we have to show that is equal to 10 over 9 times 10 to the k plus 1 minus 1, according to the formula. Okay, well, what we can do then is we can start off just taking that sum. So maybe I'll take this. Oh, I should have just made the highlighter bigger. That's okay. Okay, so let's take this and rewrite it. So we have 10 to the 1, 10 squared, all the way up to 10 to the k, 10 to the k plus 1. Now, by assumption, our assumption has those first k terms. So by our assumption, we can replace all of those with 10 over 9 times 10 to the k minus 1. And then we still have the plus 10 to the k plus 1. So now we have to do some manipulation. Well, here, this kind of looks like something where we might want to try to get like a common denominator. And so what I'll do is do some little rewriting. And basically, this 10 to the k plus 1, I can rewrite as 10 times 10 to the k, and then as 10 over 9 times 9 times 10 to the k. Okay, so that's still the same number, right? I'm just kind of making it look worse, but it'll help us here. So we have 10 over 9 times 10 to the k minus 1 plus 10 over 9 times, 9 times 10 to the k. So that gives us 10 over 9 times, and because that's a factor for both of them, we can now kind of bring them together. So we have 10 over 9 times 10 to the k minus 1 plus 9 times 10 to the k. Well, now we have two 10 to the k's on the inside. So we can write this as 10 over 9, 10 times 10 to the k minus 1, which is equal to 10 over 9, 10 to the k plus 1 minus 1. And that's it. That's what we wanted, right? This is exactly what the original statement has on the right-hand side if we just plug in n is equal to k plus 1. And then here we started off with the left-hand side for n is equal to k plus 1. And so, because we've shown that if we assume n is equal to k, we can prove n is equal to k plus 1. By induction, we know that it's true for all values of n. So I'll just write out that initial thing again. So these sums of powers of 10 all the way from 1 to n is equal to 10 over 9, 10 to the n minus 1. Nice. That's a cool one. And this kind of like way of doing the inductive step is pretty common to every single one of these where you've got a sum with a dot, dot, dot. You're always going to be like taking out a bunch of terms that are the same as your assumption and then adding the new one to it and rewriting. All right, so example number 3, we've got an inequality one. These ones can be a little trickier, but I don't know, I think they're pretty cool. So we want to prove by induction that 2 to the power of n is greater than 1 plus n for n greater than or equal to 1. As always, we start off with our base case. That's when n is equal to 1. And that gives us 2 on the left-hand side. And so we say 2 greater than or equal to 1 plus 1, which is 2. This does have an equal in it. It's not just greater than, it's greater than or equal to, so this is fine. All right. For our inductive step, let's assume that 2 to the k is greater than or equal to 1 plus k. Then what we want to show is that 2 to the k plus 1 is equal to, or is greater than or equal to 1 plus k plus 1, which is 2 plus k. So I always just write this one to show, to kind of keep in mind what we're trying to do. So if we start off with that 2 to the power of k plus 1, then how can we manipulate this? How can we get our assumption to show up? That's the thing, right? Well, our assumption says something about 2 to the k, so let's just take out a power of 2. Then we have 2 to the k, 2 times 2 to the k. And so by the assumption, we can say that this is greater than or equal to 2 times 1 plus k. Because the assumption told us that 2 to the k is greater than or equal to 1 plus k. And so certainly 2 times 2 to the k should be greater than or equal to 2 times 1 plus k. Okay, well, this 2 times 1 plus k, I can rewrite that as 2 plus 2k, And certainly 2 plus 2k is greater than 2 plus k, because we know k is positive. And then that's it. We're done. We have shown, we've got this chain of inequalities that tells us that 2 to the k plus 1 is greater than 2 plus k. And that's what we wanted. We're good. So by induction, you can say that 2 to the power of n is greater than or equal to 1 plus n for n greater than or equal to 1. I like that one. It's really just following that chain of inequalities. All right, now we have another divisibility problem. So let's keep going through this. We've got our base case, and I hope that now that you've seen a couple examples, maybe like pause this video and try the question and then compare it to what I've done. That might help. Okay, so base case. When it's all natural numbers n, we start with n is equal to 1. 8 to the power of n minus, oh, not n, we have 1. Oops. Okay, 8 to the 1 minus 3 to the 1. That's 8 minus 3, that's 5. This is indeed divisible by 5. That's good. Inductive step, we assume now that 8 to the n minus 3 to the n is divisible by 5. And now what we want to do is look at, oh, sorry, not n. I'll put k there. You could use n, but I like to just do k just to kind of make it more clear that like n is general. I don't know. Okay, so we have 8 to the k minus 3 to the k. Then we're going to consider 8 to the k plus 1 minus 3 to the k plus 1. We want to show that this is also divisible by k, or by 5, and try to get our assumption to show up. Well, here I'm looking at how we've got 8 to the k and 3 to the k only in the original assumption. And so what I'll do is something we did in some of these other examples where I just factor out one of the powers of 8 and one of the powers of 3. So that gives me 8 times 8 to the k minus 3 times 3 to the k. And now what I'm going to do is, because I want the 8 to the k minus 3 to the k like together, I'm going to go with this first 8 to the k and start a bracket. And inside that bracket, I'm going to have 8 to the k minus 3 to the k plus 3 to the k. And then here I've got minus 3 times 3 to the k. And then what I can do is keep these first two terms inside of the bracket together, because our assumption says that this is divisible by 5. And then I'm going to distribute that 8 with the 3 to the k. So this gives us 8 times 8 to the k minus 3 to the k. And then we've got plus 8 times 3 to the k minus 3 times 3 to the k. So that's 8 times 8 to the k minus 3 to the k plus 5 times 3 to the k. So now we know this is divisible by 5, this first term, because we've got 8 to the k minus 3 to the k. And so that's divisible by 5 by assumption, or by inductive hypothesis. That's another thing people say. And then this is clearly divisible by 5 because it's 5 times something. Therefore, 8 to the k plus 1 minus 3 to the k plus 1 is divisible by 5. Therefore, by induction, we can say that 8 to the n minus 3 to the n is always divisible by 5. It's missing some letters. Divisible by 5 for all n. All right. Here is another sum one. Example number 5 here, we want to prove by induction that the sum of 1 plus 5 plus 9 plus 13 all the way up to 4n minus 3 is equal to n times 4n minus 2 over 2 for all positive integers n. So, as usual, we'll figure out what our base case looks like. Base case, this is another one where we start with n is equal to 1. Then the left-hand side, let's see, because 4 times 1 minus 3 is equal to 1, so left-hand side is equal to just the 1 term. There's no plus anything. And then the right-hand side, we get 1 times 4 minus 2 over 2. So that's 2 over 2, so that's 1. We're good. Then, let's see what we can do with our inductive step. Well, assume that 1 plus 5 plus 9 plus 13 plus ... plus 14k minus 3 is equal to k times 4k minus 2 over 2. And now we want to show, so okay, this is the one that's like the n is equal to k. And we want to show for n is equal to k plus 1. So for that one, the left-hand side is 1 plus 5 plus 9 plus 13 plus, well, we'll have the 4k minus 3, but then we have an extra term, that 4k plus 1 minus 3. Okay, so that's going to be the left-hand side that we have, and the right-hand side will be k plus 1, 4k plus 1 minus 2 over 2. You know what? I'm going to just factor or expand that out here a little bit. Gives us k plus 1, 4k, oops, 4k plus 4 minus 2. Yeah, over 2. So then that gives us 4k squared plus 4k plus 2k plus 2 over 2. So 4k squared plus 6k plus 2 over 2. Okay, so now we have that simplified. We'll just try to get there. Then by the assumption, left-hand side, we've got all of those, the first bunch of terms. So from 1 all the way to 4k minus 3. We know we can just cleanly substitute that out for k times 4k minus 2 over 2. So by the assumption, the left-hand side is equal to k times 4k minus 2 over 2 plus that one extra term, which is the 4 times 4k minus 1 minus 3, or 4k plus 1 minus 3, which simplifies to, so that's 4k plus 4 minus 3, so it's just 4k plus 1. So now if we combine this together using a common denominator, we get 4k squared minus 2k plus 8k plus 2 over 2, which gives us 4k squared plus 6k plus 2 over 2. And that's what we wanted. That was the right-hand side. And so we can say by induction. 1 plus 5 plus 4n minus 3 is equal to n 4n minus 2 over 2 for all natural numbers n. Okay. Gonna keep doing 2 more new ones, and then I'll go through the class ones. Or I might do that in a separate video. I don't know. We'll see. I just want the file to crash, you know. Okay, so example number 6. We want to prove by induction that the sum of 1 times 2 plus 2 times 3 plus 3 times 4 all the way up to n times n plus 1, all of that just adds up to n times n plus 1 times n plus 2 over 3. We're going to show that this is true for n greater than or equal to 1. Our base case, the last term is the one that has just n plus 1. It'll just be 1 times 2. We don't get any more terms. And on the right-hand side, we get 1 times 2 times 3 over 3. And yeah, both sides are 2. We're good. Nice. Now, let's do our inductive step. Let's assume that the big sum given, so 1 times 2 plus 2 times 3 plus 3 times 4 all the way up to k times k plus 1 is equal to what the formula says. So k times k plus 1 times k plus 2 all over 3. Then we want to use this to show n is equal to k plus 1, which is that if we go 1 times 2 plus 2 times 3, blah, 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 all the way up to k times k plus 1 plus k plus 1 times k plus 2, or times k plus 2, is equal to k plus 1 times k plus 2 times k plus 3. Okay, so let's call this left-hand side for k plus 1, and then right-hand side. Oh, I don't know how I did that. Right-hand side for k plus 1. Okay, so, okay, I won't skip us. It's not even skipping a step. Anyways, so the left-hand side for k plus 1 is equal to this 1 times 2 plus 2 times 3 all the way up to k plus 1 plus k plus 1, k plus 2. Then, because of the inductive hypothesis, these first k terms are exactly equal to k times k plus 1 times k plus 2 over 3. So we can replace those terms because of the assumption. So we have k plus 1, k plus 2 over 3, and then we still have those that last term, that last product. By assumption. And then now, like a lot of the questions before, we'll try to do a common denominator. And I'll expand out what we've got up top too to see if we can kind of simplify it. Oh, I forgot over 3 here. Okay, yeah, so we've got k, and then k squared plus 3k plus 2 over 3 plus 3k squared plus 9k plus 6 over 3. And this adds up together to give us k cubed plus 6k squared plus 11k plus 6 over 3. Just expanding that first term and then combining them. Then the right-hand side of k plus 1, let's see what that is. take that k plus 1, k plus 2, k plus 3 over 3 and expand and simplify. We get k squared plus 3k plus 2 times k plus 3 over 3. And that gives us k cubed plus 6k squared plus 11k plus 6 over 3, just like we wanted. That's what the left-hand side of k plus 1 also gave us. So we're done. We can say, by induction, 1 times 2 plus 2 times 3, all the way up to n times n plus 1 is indeed equal to that product n times n plus 1 times n plus 2 over 3. All right. This last new one I really wanted to throw in here because it uses factorials, which I wanted to review, as well as a base case that is not n is equal to 1. Here we start for n is equal to 4. So the question is, prove by induction that 3 to the power of n is less than n plus 1 factorial for n greater than or equal to 4. So here the base case is when we set n equal to 4, then 3 to the 4 is 9 times 9, which is 81, and then 4 plus 1 factorial, that's 5 factorial. That's 5 times 4 times 3 times 2. So that's 20 times 6, that's 120. And indeed, 81 is less than 120. So we're good. And in fact, if you check for n is equal to 3, this might not work. And so we had to start at 4. Let's see what happens. For n is equal to 3, 3 cubed is 27. And 3 plus 1 factorial is 4 factorial. 4 times 3 times 2 is equal to 24. And so we don't actually have the inequality. We have that 27 is greater than 24. So that's why we start at 4. Okay. So now let's do our inductive step. Here, let's just assume that, again, for some unknown number k, we get that 3 to the k is less than k plus 1 factorial. And now we want to use that to show that 3, or I'll write it out. Okay, we want to show that 3k plus 1 is less than k plus 2 factorial, right? Because that's k plus 1 plus 1. So 3k plus 1, we can rewrite that as 3 times 3 to the k. And that's good because that matches our 3 to the k that we already have. So 3 to the k is less than k plus 1 factorial, which means 3 times 3 to the k will be less than 3 times k plus 1 factorial by assumption. And so we know that, okay, and since k, which is like n, it has to be greater than or equal to 4, we know that it'll for sure be greater than 3. And so 3 times k plus 1 factorial is going to be less than k, well, actually, we could even do k plus 2. So you can even say k plus 2 is going to be greater than or equal to 6 is greater than 3 for sure. And so 3 times k plus 1 factorial is less than k plus 2 times k plus 1 factorial, which is k plus 2 factorial, which is what we wanted. We wanted to show that 3 to the k plus 1 is less than k plus 2 factorial. And we have, using that chain of inequalities. Amazing. Therefore, by induction, we can say that 3 to the n is less than n plus 1 factorial for n greater than or equal to 4. Wonderful. Okay. I'm going to just pause this and start a second video just so that the file isn't too big. But I hope you like these new examples, and I'll go do the other ones.